following demonstration, we'll perform a structural analysis on a full authority digital electronic control box using Simcenter 3D. Here you can see we have an assembly of the electronic box with supporting brackets mounted on a case. Here we have the ability to interrogate the geometric properties as well as mass properties of a solid body if materials or density is assigned. We'll begin creating a structural finite element analysis model of one of the brackets. The first thing we'll do is create a mid-surface representation of the bracket. So to do that, we'll first get an associative copy of it and then mid-surface it. And what you'll notice, the mid-surface representation has the gusset extended. However, it does have some geometry issues where the butt weld did not quite meet up exactly correctly. But you'll see how that's easily resolved. So we'll bring the geometry for the mid-surface and the solid into the FEM, where we'll stitch the model together. And this will allow us to fix any tiny issues with the geometry, as well as ensure a congruent mesh across the various bodies. So here we'll take a distance measurement to see just how much slop there is in the model. So 40,000 should be able to take care of that 17,000 slop, and here you can see it does, as well as ensuring a congruent mesh across the gusset. Alright, so here we'll create our shell mesh, and at first I'm going to turn off attempt to fix failed elements to show some of the element quality checks that we can do in just a moment. So here you can see we have a shell mesh on the mid-surface representation of the bracket. We can do a duplicate node check, but this really isn't necessary because we stitched the model. You can see that there are no duplicate nodes found. Another thing we can do is take a look at element free edges. And not only the free edges, but the non-manifold ones as well. Non-manifold will be displayed in cyan, the free ones in magenta. Non-manifold meaning that it ensures a congruent mesh across multiple elements. Alright, so since our shell mesh looks good, let's go ahead and do some mesh refinement first around the hole, where we'll create a mapped hole. Here we can specify the layer depth, number of layers, and size. That looks better. Next we'll, anticipating some high stresses around the mount holes of the bracket, I'd like to refine the mesh on the left or the bottom edge of the gusset. So here you can see we've done a bias on edge, so we've got a finer mesh down towards the holes and a coarser one as we move away from it. Alright, next we'll do an element quality check, and we'll use element type specific values. And here you can set whatever you want or take the defaults, the various element types, and various types of checks. So here, after we've performed the check, you can see that 7 elements have failed the element quality check. One of them has failed because of max interior angle, and 7 on taper. We can also see those elements highlighted in red in the screen, and there's also a group, an output group that was created of them. So if we wanted to just take a look at those elements by themselves, we could. so to fix those elements, we have a shell mesher that can automatically fix failed elements based on a number of different criteria, such as taper and max included or min included angle. Some of the failures that we saw. Let's go ahead and turn them all on though. And you'll see the mesh updates. And if we perform our element quality check again, we'll see that there are no failed elements down in the bottom towards the middle on the Q line. You can see 0 failed elements. All right, so next we need to assign a material, and if the designer had done that, which the designer did, we can inherit that material and not worry about specifying the wrong material. However, if we'd like to override it, we can easily go into either the material library and select one, or create one from scratch. And here you can see we have thermal, strength, and mechanical properties, Young's modulus, mass density, and we can specify whatever material we'd like. All right, so we did not specify material. We also did not specify a mid-surface thickness, which we can inherit from the mid-surface. So that way it reduces or eliminates another source of error in assigning a thickness to the shell mesh. Here you can see we can display that either as a contour or as a 3D thickness, and we can compare that to our solid representation of the bracket as well to ensure that we've got the thickness inherited correctly. So thickness, both thickness and material can be inherited and were for the bracket definition. All right, next we'll go to the FADEC. We'll create our simulation model for it. And I'm not going to bring in any bodies into the FEM yet because I want to create a mid-surface representation of the electronic box here. So first we'll create our associative copy of it. Now we've got some bosses on there that we'd like to remove, as well as a bunch of holes on the board itself that we don't need for purposes of the simulation. We'd like to get rid of some of those small holes. In order to see those holes and the board a little bit better, I'm going to clip off the top of the box so that we can see inside. And that's just a view clipping section. We didn't actually subtract anything from the model. And here we can idealize away the holes based on a diameter. So here you can see as we increase that diameter, the number of holes that we are selecting is increasing, and we just want to take out the small holes. So we'll leave that diameter small, and you can see all those small holes have been removed. We can now turn off our clip section, and next we'll take care of the bosses on the outside of the box. We'd like to remove those, so we'll select the boss or pocket faces and just drag a box around the bosses, and you can see it removes them. And we'll do the same thing on the other side. This is a little bit more tricky because there is some other geometry that's right adjacent to it that we don't want. So I'll hold down the Shift key and deselect one of the faces there. All right, and that looks good. So now all our bosses are removed and we're ready to mid-surface. And here we have a toolbar which tries to predict what commands we'd like to use, and that can be very helpful so you don't have to dig through the various ribbons to find the command that you want. And that predictive toolbar is on the right there. So here, let's bring in the mid-surface and the board components. And we'll start with the board components. And what we'd like to do is create a concentrated mass representation of those components. And to quickly and easily do that, we have an option to create a lumped mass at the center of gravity. Go ahead and select all of the board components. We can select whether we want to combine those all into one, which doesn't make sense. We'll make individual masses for each. And then we'll hide the solid geometry, and we can see all of the properties that were automatically assigned, not only mass, but also the mass moment and products of inertia for that solid body. So you can see that one's about 0.64 pounds, this one's 9.96 pounds, and our last one is 0.38 pounds. All right, so next, to ensure that we have, or we'll get a congruent mesh, when we go to mesh, we'll go ahead and stitch as we did with the bracket. Now you can see the stitched edges in black, free edges in magenta. And now we'll go ahead and mesh with a slightly larger element size than we did with the bracket. And we'll only select the outside of the box. We're not going to mesh the board just yet. Now for the outside of the box, we could inherit that material if the designer had specified it in the master model. Or for this example, we'll go ahead and select a material out of the library. We'll assign titanium alloy, and we'll name the collector to denote what material is in it. And we'll also inherit the thickness from the mid-surface, and since this one has some different thickness regions, we get a little bit better, more interesting contour plot. You can see the different thickness regions on the outside of the box. All right, next we'll create a nodal coordinate system, and we can specify either reference or displacement or both. And here we'll do reference and displacement. And we'll use the same coordinate system for both reference and displacement coordinate systems. And we'll specify it using the CSIS operations in Simcenter 3D by specifying an origin plane for the z-axis to be normal to, and then also a y-axis direction. And if we don't like the direction, we can reverse it very easily. And now our CSIS has been created. All right, so next we'll go ahead and mesh the board. Let's go ahead and clip off the top of the box so we can see in a little bit better. And we'll use the same mesh parameters. We'll select the face of the board. All right, and then we can go ahead and check our element quality. But since we had the auto fix on, you can see there's zero failed elements. But if there was a failed element, we have some other things we can do to fix it. We can split a quad into two triangles. There's also a number of different types of ways we can split shells. And we can also drag a node along geometry while having an element quality check on. So here you can pick your favorite element quality check that you'd like to see, and that will be displayed while you're dragging. Also, if you violate the threshold values for any of those, you can see it will change its color from green to red. All right, so let's go ahead and assign a material to the board. Here we'll pick epoxy out of the library. And for the thickness, we'll go ahead, the same as before, and here we'll name it first, and then we'll assign a thickness inheriting it from the mid-surface. All right, and then just to double check that we've got the assigned materials correct, we can change our color display to show what materials are assigned to what meshes. So there you can see our epoxy and our titanium alloy are correctly assigned. All right, next we'll connect our board components into the board using RBE2 elements. We'll do a point to face connection. And we'll go ahead and save. All right, next we'll go ahead and do some brick meshing on our fan case. We'll begin in our idealized part, creating an associative copy of the case. And then we'll idealize the blends. Here we're using the predictive toolbar for our commands. So here in the same fashion for blends, we can have it find the blends based on the size. So we'll go ahead and remove blends less than or equal to 1/4 of an inch in radius. All right, next we'd like to remove the drill points on some of our blind holes in one of the flanges. And we could use the delete face and then go ahead and pick each one of those faces, but that's a bit tedious. Better method is to use a filter. And we'll say that we'd like to look for faces that are conical, and then just drag a box and it will find all of our conical faces, and then we can delete them. All right, next we'll do some splitting to ensure that we can create a swept mesh on the body. Here you can see we can check for sweepability by the software will automatically color code those objects that are not sweepable or that it thinks are not sweepable as red, and those that are will be colored green. So here we can keep continuing by splitting the body by a plane, which we're defining on the fly, selecting the face to define the plane. All right, and then if we go back into the split body command and turn on check for sweepability, you can see all of our bodies are green, ready for swept meshing. So now we'll go to the FEM, bring in the bodies of the case. And to ensure a congruent mesh across our solid mesh, we're going to create glue coincident mesh mating conditions. Here you can see we have an automatic algorithm where it will go through and find faces that match within a specified tolerance. We had it set at 1/1000th of an inch. Here you can see the 5 glue coincident mesh mating conditions that have been created. Alright, so now when we create our sweat meshes, we'll automatically get congruent mesh across the various bodies that we've split up. So here we're going to sweep until target from 2 source faces to 2 target faces. No need to create any additional splits in order to create a sweat mesh on that flange. Next, we'll select a multi-body where we can do 2 at once, and we're going to mesh all of these into the same collector since they're all the same material. Alright, next we'll do an until target from 2 source faces to 1 target. And the same thing on the other end, 2 source faces to 1 target. And if we just wanted to look at one of the bodies at a time, we can do that also with a show only command. So here we'll show only the end body here, and you can see that it's divided the face up based on the mesh mating conditions that were created. And we'll do until target, and we'll box select to get our 6 source faces, and then select our single target. All right, then we can show all again, bring back the entire model. And here, if we want, we could assign a unique material, or we can just inherit it from whatever the designer had set in the master model. All right, now if we want, we can also do a duplicate node check, but since we created mesh mating conditions, this is not necessary. No duplicate nodes were found. Now, if we wanted to select elements by their type, what we could do is run a journal program which will create groups of elements based on their type. If they're a wedge element, or an 8-noded hex, or a 20-noded hex, it will create groups for all of the different element types that you have in your model. So here you can see all of your wedge 6 elements. It's created a group of it. We can show only that group if we want to see just the wedge elements, and select just the wedge elements. All right, so now we're ready to assemble all of our finite element models. For that, we'll create a new assembly FEM. And here you can see all of the component parts that make up that assembly. And we can automatically map the finite element models of it to it. So now we did not do the fan case because we don't want to include that in our structural simulation model. But if we wanted to, we could have included it. I've ignored it for now. And you can see the multiple use brackets have all been brought in their correct locations based on the assembly structure and positions in the design model for the assembly. So next we'll create some 1D connections to help us with specifying some constraints in just a moment. And we'll create a point-to-edge connection. From the holes of the bracket to a central node. And now, because we've assembled a number of finite element models, there are some conflicts with nodes and elements and physical property, table numbers, and we can easily automatically resolve those conflicts based on a number of different algorithms that we can select up top there. Or we can manually assign an offset as well. If we know we want a particular component to have a particular node and element range, we can assign an offset for it manually. All right, now if we'd like to find a specific element or node, we can find it by its label, by its element number. And sometimes it may be difficult to see, well, now where is that element that we just identified? If you go to an unshaded view, that helps. Also, zooming back helps because the label doesn't change size even though the model does. And then once you've identified it, go back to a shaded view to see the element in better detail. Once we say OK to the dialog, we'll get more details on that element in the information window, what type of element it is, what nodes it's connected to. All right, so now that we've assembled the various finite element models, we can create a new simulation file. The simulation file is where we'll create our solutions and our constraints. So here we'll create a Nastran solution 101 linear static, but you can see we have quite a few different solutions we can choose from solution 111 modal frequency response. We also have solution 401 multi-step nonlinear, but we'll just go ahead and create our solution 101 linear statics. We'll call it S101, and we'll also specify we'd like some specific output requests for grid point forces and glue. So here we'll turn those on. And we can also preview all of the output requests that are selected. Here you can see we're also going to get displacement and stress, as well as SPC forces. All right, so let's begin by connecting the bracket to the box. We have a couple of ways we could do that. We're going to use glue, and we do have an automatic pairing algorithm, but that's usually better for parts that are closer together that you'd like to connect. When they're a little bit further, it's better to control a little bit more closely exactly what faces you'd like to define for your source region and what faces you'd like to define for your target. So for our source, we'll pick some box faces, and for our target, we'll pick some bracket faces. Then we need to specify a search distance. Any faces that it finds within the search distance, it will glue. If there are faces outside of that search distance, and here I've measured, you can see it's 0.65 away. If we do 0.7, we'll be able to capture the box and the bracket together with some glue. All right, next we'll assign some loads, and for our first subcase, we'll rename it temperatures because we're going to put a temperature load in there. So I'll create my temperature set, specify a default temperature, 68 degrees, and then put our temperature load inside that temperature set. The temperature load is coming from flow EFD. We ran a thermal analysis there, and it wrote out temperature field data in the form of X, Y, Z, and temperature. So we'll import it as a field, Cartesian, and also the location of that data does not correspond to our model. So we need to specify a coordinate system that aligns with the data and our model to adjust the position. And we can select our interpolator and then also import our field data. And if there's any duplicates, we can choose to find the average or the first. Also, our data was in the format of inches and degrees centigrade, so we can easily change that field from Fahrenheit to Celsius. All right, so here's our data. You can see it's imported quite a few rows of data there, and we'll apply it to our entire assembly. Now we can plot to see how those temperatures will be mapped based on our interpolation algorithm that we had selected with Delaunay Fast. So here you can see the temperatures mapped onto our mesh, and that looks right. We've got some dissipation from the various board components. You can see heating up the model. Now we can also view the raw field data as the field that it is to ensure that it is in the correct location as well, but that is not the mapped data. That's just the raw field data. All right, so now that we've created our temperature subcase, let's create a gravity load subcase as well. We'll create a 1G load in it. We'll call it 1G. And here we can specify whatever units we want. We'll put it in G's. Here you can see the direction, minus Y. Looks good. And we don't need to select any objects to apply our gravity load. It'll be applied to the entire model. Next, we'll create a constraint at our central node there. Now we can also take a look at our simulation summary. It will give us information as to the mesh summary. Here you can see the total number of elements and nodes in the model, as well as the types of elements that are in there. It'll also show us what types of solutions we have, as well as our loads and constraints. All right, next we can also get the mass properties of our mesh by doing a solid properties check, and I'm just going to select the elements that are the box, but not the bracket, and also everything in the box, including our concentrated mass elements for our board components. And here you can see the total mass. Let's go ahead and copy that and paste it into Excel. And then let's multiply it by G in order to get a weight. So 13 pounds, that's how much our electronic box weighs. Let's remember that for later when we take a look at our results. Next, we'll take a look at our solver parameters. Here we can set up parallel SNP as well as DNP, single memory as well as distributed memory parallel. We can also set advanced solver options for what units we'd like to write the deck out in, as well as assembly options. since we have an assembly FEM, we can have it retain part hierarchy, including using include files. And we can also have it compact material data. Since we have 4 brackets, we can compact the 4 materials into 1 material. And now we'll go ahead and solve. This takes about 5 seconds or so to solve for a linear static solution. Here you can see we get a solution monitor that counts the time in the bottom right hand corner, and about 7 seconds it's completed. Now before we take a look at the results, let's take a look at what the deck looks like. If we go ahead and open up the top level deck, here you can see the file management, case control, and bulk data sections. And the bulk data section, here you can see, has an include file which points to the FEM, and then it just has the loads and constraints. No other nodes or elements are in there. Now if we dig down into, take a look at the assembly bulk data file, here you can see the include files that point to the various components that make up that assembly, as well as the RBE2 that we created between the brackets and the consolidated material for the 4 brackets as one material card. And then here, let's take a look at one of the bracket bulk data files, and you can see the nodes and elements and P-shell for it. All right, so let's go ahead and take a look at our results. We'll begin taking a look at the displacement results for our temperature subcase. And here you can see about 20 thousandths max displacement due to the temperature. You can animate those results. You can also take a look at the stress from the thermal load on the model. And then we can also take a look at our displacement from our G load, our 1G load, displacement and stress. And then as a double check, let's go ahead and take a look at our glue force results in the Y direction. That was the direction of G. And we'll go ahead and identify the results on the feature faces of the brackets. And here you can see the sum is 13.0 pounds. Same as what we had found from our solid properties check. So that's a good double check. We can take all of this data and put it into Excel so that we can further analyze the data. You can see the node location, and XYZ glue result for it. At the bottom, you can find the column sum, average, and weighted average, and we were looking at column Y for our 13 pounds. All right, so let's say we really want a 10G load with our temperatures. How can we do that? Well, we can create a combined load case by specifying a scale factor for each of the various subcases. So here we'll select a 10 scale factor for the G load and 1 for the temperature. We don't need to solve again. You can see that we've got those results. Here we can take a look at displacement. That's displacement in the Y. We can look at displacement magnitude as well. You can also see our stress results due to the 10G load and the temperature load. And what you'll notice is the stresses really are highest, as you'd expect, right around our constraints. But maybe we don't want to include the loads right around our constraint. So what we can do is take all of the results that are above 20 KSI, and we've got a peak stress of 34 KSI here, and put that into a group. And then we can hide that group to turn off all of those elements that have stress above 20 KSI. And then we can see what the contours look like with a max stress of 20 KSI. We can also clip the results above a certain amount as well. All right, we can also take measurements. It's best though to be in an absolute one-to-one displacement view as opposed to an exaggerated 10% displacement view, which we were in before, in order to get accurate one-to-one measurements of the deflected view. So here we can select nodes and see what the distance is between those nodes. All right, and then as we could in modeling, we can also in post create cutting planes and clip the model so we can see better what's going on inside. They don't have to be planar. Here's a cylindrical clipping plane that I defined to allow us to look in and see what's going on a little bit more clearly on the board inside the box. All right, so here we can turn on averaging, see our average stress. And also maybe we want to just take a look at the one bracket and get rid of all of the other components. And next what we'll do is we'll create a graph of the stress along a path. Here we'll define a path along the bend of the bracket. And then we can plot the stress at the points along that path. And then we can also create a free body if we have grid point results, which we do. So here we'll create a free body result across the butt weld in our bracket, see what kind of load is going through it. Here I'll select some elements on one side of the butt weld and the nodes along the butt weld joint. Here I can select location to sum the moments about, and then here you can see our forces will be in red and our moments in blue. So you can see our force is about 89 pounds and its direction, and then moments about 14 pounds. At that node that we had selected. All right, so next we would like to create a random analysis. We could do a solution 111 modal frequency response, but we have a much more efficient way of doing that with our response dynamics solution. First we do solution 103, response dynamics solution, where we tell it how many modes we'd like to recover. And since we're not really sure exactly how many modes we want, we'll just select a range from 1 to 2000 hertz. And then also, because we want to do a random analysis, we'll also specify that we're going to be setting it up for a random base excitation event. All right, and then we can reuse the glue that we had created from our linear static solution, as well as our temperature load, and this can be used to adjust the material properties for the modal analysis if they were temperature dependent material properties. And we can specify our enforced motion location. And we'd like to enforce motion in all three directions. And then we'll constrain rotations with a user-defined constraint. All right, so at this point we're ready to solve. And this solution takes about a minute. While it's solving, what we'll do is we'll take a look at the input PSD that we'd like to use for our random analysis. We'll go ahead and load that up. Here you can see we have PSD in the three directions. And what we'd like to do is add more points between the 4 breakpoints that are defined in that PSD. And we can do that by interpolating with a number of different methods. And we'll select the linear log, linear being x and log being on the y-axis. And it creates a new function with a lot more points, basically 1 point for each hert. Now, if we plot the original function first and interrogate it, we could also take a look at the raw data, but here we can see it on the graph. There's just 4 points in our PSD-Y. If we take a look at the PSD-Y lin log plotted with it, you can see how it interpolates between those 4 points. And now on the y-axis we have a linear axis, so you can see a difference between the PSD-Y and the PSD-Y lin log. Now if we change the y-axis to be logarithmic, the 2 curves are going to lie right on top of each other. So here you can see PSD-Y and lin log are basically right on top of each other. And if we go ahead and probe, here you can see that it lies right along it. All right, but we don't actually need that. The random base excitation that we're going to perform will use a logarithmic interpolation. If we wanted to use a different one, we could create a synchronized function and use that instead. So here we'll create a new response dynamics solution, and you can see our 123 modes that were recovered, as well as the total effective mass in the X, Y, Z, and rotational directions. If we didn't have enough, we could get more modes. Here we'll go ahead and specify a viscous damping factor of 2% for all the modes. And then we'll create our, actually first let's take a look at the transmissibility in terms of acceleration of a point on the board in the Y direction. So here I'm just picking a node somewhere in the middle of the board, and we'll evaluate the transmissibility between 0 and 2000 hertz. Actually, I guess we'll do 200. We can select how we'd like to interpolate, and here we can see the results. All right, next we'll create our random base excitation event and define what output we'd like to look at. By default, we're going to get accelerations, but we'd also like displacements for contours as well as for XY plotting. I'll pick a node on the middle of the board, and then we'll just get stresses for contours. Now also we need to specify the number of standard deviations for our results, and if we select 1, that will give us RMS for our results. If we select a higher number of standard deviations, that would give us more confidence with what the peak stresses or displacements are. Here we'll go ahead and specify our excitation PSD and our enforced motion location, and we're ready to solve. And this is a real-time solve. It's about 6 seconds that it takes to get the displacement and stress and acceleration results here. And you can see all of those results plus the XY plot results. And we'll start with displacements. Here you can see our RMS displacement results since we asked for 1 standard deviation of confidence. Here we can see the VM stresses. That's RMS as well. Now, if we'd like to just take a look at the stresses on the board, let's go ahead and turn off the brackets, and also we'll turn off the displacements to 1-to-1. And here you can see we've got all of our meshes available in the post-processor. Let's turn off the titanium, which is the box, and just leave the epoxy. And we'll get average stress, and we'll go ahead and turn off the feature lines. So here you can see our RMS stress on just the board. All right, now we can also take a look at the PSD output plots for displacement that we had requested, and it's not under the that's the transmissibility curve. Here's our PSD output. So here you can see translations in X, Y, and Z and rotations about that node that we had selected. Let's go ahead and change our Y-axis type, and there you can see our PSD output at that node that we had selected on our board. And there you can see the RMS displacement there as well. All right, so now that we've completed our random analysis, we'd also like to do a drop test on this board. So let's go ahead and set up a transient event. We'll call it drop test, and we'll define a velocity impact excitation. And this will be a drop impact method, and we can specify the time step. And when we change the drop height, what you'll notice is the velocity will update based on our drop height. So we'll specify a drop height, which will imply a velocity and a pulse duration. And we'll start our analysis at impact. And we'll begin by taking a look at our peak displacement results. And we're really interested in displacements just on the board, so I'll just select the feature angle nodes, selecting one of the nodes on the board, and it will get everything on the board. We'll look at the displacement in Y, and we also want it relative to the node that is our excitation node. So here I'll pause the video. It takes about 20 seconds or so to get our board displacement results. Here we can take a look at those. And here you can see the max displacement is about 1/10 of an inch. And we can also find the node that is seeing that max displacement, 1167.12. 116.712. So let's go ahead and evaluate our function response for that particular node as a function of time. So here we can just go ahead and type in that node. again, relative to our excitation node. And we want to take a look at those results in Y. All right, and there you can see that 0.1 as the max. You can do a peak probing mode to make sure we see exactly that max and what happens as a function of time. All right, lastly, we'll take a look at our peak stress on the board as a result of our drop impact from 36 inches. All right, that one takes about 8 seconds. And here you can see our peak stress on the board due to our drop impact. Now let's go ahead and save everything. And now we have a CAD change. One of our components, the bracket, is based off of a JT file that came in to us from a third-party CAD package, such as CATIA. So to incorporate that change, we'll go ahead and close the bracket, and then we'll swap out the JT file for the bracket, call the one that we were using -old, and our new one, which is the BREV, we'll call that the same thing, so that when we open up our bracket PRT file, which points to that JT, it will automatically use that data. And it will use it in an associative fashion so that we don't have to start over from scratch with the definition of our bracket finite element model. So let's go to our idealized part. This is where we created our mid-surface, and you can see that that has updated to incorporate the lightning hole in the gusset. Next we'll go to our finite element model. You can see that the mesh does not correspond to that geometry change until we hit the update button. At the same time, it's remembering our mesh controls, our mesh thickness, and physical properties that were inherited to it, so we don't have anything left to do on our bracket. The change did not affect the electronic box, the FADEC, so we have nothing to do there. Let's go to our assembly FEM, and because we had a mesh update, you can see that the node and element numbers have changed. All we have to do is go ahead and resolve those conflicts for the nodes and elements. Hit the automatic resolve. Now, instead of just solving the existing solution, I'm going to go ahead and clone it so that we can look at our results side by side. And I'll call it S101A, and we'll go ahead and solve. I'll pause the video, and in another 6 or 7 seconds we have our updated results for our brackets with the lightning hole. And we can take a look at those side by side, and we'll take a look at our 1G load stress results with the lightning hole side by side with the 1G load from our original model without the lightning hole. Here we can synchronize the views. So that when we rotate or zoom on one, it brings us to the same location in the other model. And let's go ahead and take a look at average stress, and maybe turn on the contour lines as well. All right, we can also turn on the annotations to see where the max is occurring and evaluate the performance implications for our change very quickly and easily. And that concludes the demonstration.